tells me about the first 5 minutes when people join in. Okay, so as I promised, today will be lighter. We talk about basically what is computer architecture. The reason why I have to say this is because it's one of the area in the country that's really, 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 really lacking, right? There's not a lot of people who focus on this. Anyone here heard about the word front end and back end and full stack developer? Right? And somehow there's an impression that if you can do like full stack developer, you are the god, right? Surprise, your back end is my front end. So, so that's the front end of me because when I develop the system, when I develop the hardware, I need to think about what's running, right? So these things, if you want to go into web development, it's great to know the back end, quote unquote, their back end, which is how to deploy application, right? But if you know how the system actually manage things you deploy, you can do things faster, you can save costs, you can make sure things doesn't crash. And today I'll give you quite a lot of example of things in real world in this country that has been crashing so far, right? So hopefully today is fun. Not a lot of things we cover today will go on to the exam. So relax a bit. Everything that goes on to the quiz probably will start the second lecture. The reason I've said the word probably is who knows. But before we begin, right? So I need to tell you what you're getting into. It's a requirement for the graduation. So we're not gonna make the basically assignments to focus on the hardware side. I do not expect that all of you can say finish this class and design certain piece of hardware, right? That's not my expectation. I'm gonna talk about some of your expectation. Recommend reading. I'm gonna put in the list, and you might have found it already on syllabus that the first link for this class is a blog post by one of the computer architects. He's working at Google right now, and he wrote basically it's like a brief history of our area, computer architecture, and the article put in the context of old design that at the time is way ahead of their time. So it didn't actually materialize into an actual machine that works, but somehow some of them actually appear nowadays, right? You might have heard about the word TPU, Tensor Processing Unit. That's a really old idea that is way ahead of the time called systolic array. You might have heard of the GPU. Okay? The GPU is being done to run games, right? And these days we run deep learning. Right? Again, it's being invented way earlier using multiple techniques and again ahead of the time, right? Additional material, as Ajahn Sanson pointed out in the first lecture, right? I recommend Hennessy and Patterson. By the way, both of them just got the Turing Award a few years back. This is actually one of their contribution to the field, right? They established this like quote unquote default textbook that you would all go to. The problem is don't dive in right away. I really recommend you not to dive in right away because they assume I would say material that being taught in computer engineering degree, which means that you will need to know some circuits and some of the digital design, the basic ones, right? So some of you might have heard about it, some of you might not. So if you dive in and you see terminology like I don't know what's going on here, check with me. I can answer it for you, right? So my recommendation here is if you want to actually dive into the topic, feel free to reach out to me later. Everything we learn in class will be just from the lecture material, right? I'll make sure everything is understandable. Everything is done based on your understanding of a computer so far in MUIC. And I'll make sure I abstract away the hardware side. All right, admin stuff. Quickly, briefly, you all know me, right? Been at TGS in KMUTNB since 2019. But the reason I introduce myself again here in this class is this is my field. Computer architecture is basically my playground. You can check out what I've done. I designed the GPU. I designed the thing called network on chip. Basically, let's say you have multiple processor in one CPU. How can you actually make them talk to each other? I look into virtual memory. I would say, the handful of researcher in the world who actively look into how to make virtual memory faster. I look into a little bit into high performance computing, file system, and storage system for mobile phone, in collaboration with a team from Hong Kong and Huawei. I also look into how to virtualize things, how to actually deploy serverless architecture, which is different from a traditional cloud. If you're curious about it, check with me later. It's totally fine. Uh, you all know how to reach me, and my thesis is basically how to make a better GPU. That's my thesis when I was at Carnegie Mellon. Uh, I was told that some of these design actually can be pretty interesting. Some of them are actually kind of like the similar ideas already implemented in the NVIDIA GPU. Not exactly, definitely not the exact same idea because we actually don't know. They don't have the white paper on that. But after I present some of my work at a conference, I was told by people from NVIDIA that, hey, these are interesting, right? Uh, so a bit more about you, right? So this is some of the things you can nod your head. You can say yes or no. You can basically use the emoticon over there on the WebEx that is already provided by default. Have you heard about the ISA? Somewhat, right? Assembly, sure, yes. Sick of it. Cache, sick of it. X86, probably also sick of that. Uh, TPU, Tensor Processing Unit, Tensor Core. Have you heard about that? Anyone here took deep learning before? The deep learning class at MUIC? So if you are taking the class, right, you might be using PyTorch or TensorFlow. So if your machine happen to have a fancy GPU that is costly right now, so don't buy it yet. Right now, I think it's way overpriced, like way overpriced. Wait until this Bitcoin mining thing dies down a little bit. It happened like 5 to 6 years back, and it's gonna die down for sure. When the price go down, people will use a different things to mine Bitcoin again, right? But these are really, really specialized hardware for you to do deep learning. It's gonna make deep learning really, really fast. The GPU, right? So how many of you here play games? Okay. Didn't know about. I know that China banned Bitcoin mining, but I didn't know they're selling their cards. By the way, don't buy those cards. My recommendation is don't buy it because because these cards are being overclocked and overused. They're not designed to run 24/7. Right? So you're gonna get a card that's likely to like die earlier than expected time. Yeah, they abuse, uh, ish. I mean, when you heat things up, right? Yes. There's a thermal element, right? Have you seen clips where you can fry things with the some of the mobile phone? I'm sure some of you've seen it, right? You can grill things on a mobile phone chip, right? Think about actual metal and silicon and everything that goes on the chip. And if you have to heat it up to that temperature 24/7, right? Yeah, you are basically making this material dying faster. It is not designed for that. Yeah, but you've heard about the GPU, right? You use it to play games. We all use it to enjoy the like rendering on Netflix, on YouTube, right? 4K, basically, yes, grilling professionally in it. It's actually not that hot, actually. If it's too hot, have you anyone here tried overclocking before? So one of the things that can end up happening when you overclock is you overclock too fast. So the temperature go too high. There's a sensor on your motherboard that checks for the temperature. If it's way too high, it shuts down. So sometimes if you overclock aggressively, one thing that can happen is your computer shut down, right? It can happen. It's a safety net to make sure you don't literally melt your chip, right? So it's there as well. Uh, you might have heard about edge device or IoT, right? There's a big element of computer system inside the edge device or IoT. To be honest, if you take the undergraduate level IoT classes, you're gonna focus on one single device and how to program those microcontroller, which is really, really important. But think about what if you have to connect thousand and thousand and thousand of that? That's a question that I believe many of people, at least engineer in Thailand, never consider, and they claim they are doing IoT. And this can be something that would actually crash the system easily, right? Crash the system easily. So think about it when you graduate and work on like, hey, work on IoT. Make sure they are scalable. Make sure you can connect like thousands of these. Because at the end of the day, if you want to work in smart city, right? Just just think about example like if I have a smart parking lot that I can communicate and send the status of like whether there's a car in the spot to my app, right? But what if I have to control like 10 different buildings at the same time? How can you how can I control that cheaply, right? And reliably? It can be quite challenging, right? Cloud and serverless. I'm sure you heard about cloud, right? By this point, basically it's like a AWS. You can rent a time on this big server, right, and run things. You can look into serverless computing, which I don't think the service available anywhere in Thailand yet. I mean, you can use Amazon service, but like a company that's claimed to do cloud in this country, I don't think they're capable of doing serverless at all, right? But these are microservices. Basically, these are, let's say I have a function call that I want to run, but I don't want to run it on my machine. I want to run it on the cloud, right? Instead of hiring a full stack developer who can configure the hardware, would deploy a database and run your application, right? And from the front end side, I just want to run these things. The rest, I'll make sure the system handle that. I'll make the system handle that. So the cloud, like Amazon, Google Cloud, Microsoft Azure, right? They all have to configure that automatically for you. And how can we make it programmable? How can we make it fast? So these are actually system topics that if you know about the hardware, if you know about the system, basically the material that Ajahn Sansan taught you guys, and if you know a little bit of the network, the material that Ajahn cannot taught you guys, these are things that you can expand into. These are the new world that many computer engineer in Thailand never seen before, right? And if you want to push the frontier of technology in this country further, you must, I think it's a must. You must know at least some of this, right? And the goal of this module is, well, to integrate with the OS and the network part. But now let's look at the computer as the piece of hardware and know how it works. Know what happened when you run a program, right? And be a better programmer, but not from the algorithmic sense. I'm not gonna tell you this is the best algorithm and how to design the best algorithm because I'm not the expert in that area. You all know who is the expert and who you should talk to. If you don't know, go back to your earlier module and that guy is the expert. Uh, think out of the box, right? Many of you might not consider this, but you can optimize the code knowing how the hardware works, and Project 3 will be designed specifically for that. We'll make sure that if you know the size of the cache on SysQ, if you know the size of the L2 cache on SysQ, you can write a program that is a lot faster. And you know how many processors are available for you to try on SysQ, you can write parallel program to make it fast using pthread. If you, hopefully you're not sick of it so far. I think many of you might be sick of that, yeah, so far. But the program that you will be writing is not gonna give you a lot of error. I think it's just a matter of organizing the data. Um, hopefully. And the other thing is, let's say you enjoy this module and you go full blown do the architecture, right? You can change your hardware. And these days, there's many instances of people changing the hardware to specifically design for certain features, right? So what do I expect from you? Well, hopefully you all know C. Hopefully by this point, you are sick of C. And attend lectures, simple, right? Do all the required work and work hard. I think you've been doing really good so far. And yeah, C++ is better. I agree. And no, you cannot use Rust. Uh, any more comments about the language? You see. Um, And the reason I put the word work hard is I feel like by default for this class, you already experienced that. So we'll slow down a little bit. I think the last module is it's gonna be a little bit easier compared to earlier projects. Uh, wait, what? Uh, oh, who knows? It might be good too. I mean, I've seen your solution, right? Guys, I think you underestimate yourself, right? The reason why I enjoy teaching at MUSC a lot is like you guys are good at learning. And that you guys are good at like working together, trying to find the answer. By not copying, by the way. If you've been copying so far, well, not nice. That's an easy way to get you fired once you actually in the job market. Ask questions and participate in discussion. That's how we can make it fun, right? It's the best way to learn. Well, just put in the chat. I read the chat all the time while I'm mumbling through my lecture. And do not procrastinate on your assignments. As you can see, it's already been bumped. Project 2 deadlines already bumped by a couple of weeks. So I want to make sure we all submit project 3 by the time I need to submit the grade. All right. It's not too hard, but it can be kind of confusing when you involve pthread at the last segment of the last project, but for the different purposes. So I think this one would be a lot easier, right? And these are all easy. The reason why want to make sure you attend lecture is this. We're gonna go fast, faster than system skill for sure, right? And because it's only basically 7 lectures, we'll go through multiple material and want to make sure you are aware of things that are going on in hardware that impact performance and impact things like energy, right? So these are quite important. And don't be scared, it's not that bad. How bad can it be? All right. You'll be fine. I taught you all. I mean, come on. I think you're fully capable of basically finishing with the really all the things done, right? All right, collaboration policy, same deal with system skill. It's okay to brainstorm to reach the solution, discuss high level direction, using whiteboard or I guess some way for you to kind of like draw things. I know it is all back online again. It's not optimal, but well, yeah. Not okay to copy your friend's code or look at your friend's code unless your code broke, your friends come in and trying to with you figure out what can break this. And together you ship in. Don't say, hey, work on this for me. Right? That's not good. That's not even a nice way to treat other human being. And I don't tolerate plagiarism of any kind for this particular class because it's more advanced, or I'm going to be a little bit more serious about this. So I'm going to get 0 for the assignment if it's clear that you're copying code. All right, and the last project is on code optimization. So don't be scared. I'm going to give you a functioning code. Basically, everything is function. That's your baseline. Your task is to write it so that the cache hit rate is sky high, right? So I'm gonna, on the assignment sheet, I'm gonna tell you how to determine the cache size of the system. There's a command in Linux that you can type in, you print out the processor detail. I test it out. It works on system skill, right? The only thing that might impact this a little bit, so that's why I'm not sure if I'm gonna make it a challenge to like see who is the fastest, is if you're running and your 5 other friends also testing your program because it's like the last day of the deadline, you might see interference because your friends will make your code slower because they get scheduled at the same time. So this can happen. Make sure you kind of like factor that in when you run your program. I'll make sure that when I test the program, I loop around this testing 10 times at least, so I can average out the total time. Right, so it should be amortized. It should be kind of average performance of your code. So that's the first task, improve the cache hit rate. The second task is parallelize that. We are looking into block metrics multiply. The beauty about metrics multiply is you can do that in parallel. The second beauty of metrics multiply, it used a ton in deep learning. So if you know how to do this, you can extend it to writing this on a GPU, and you then know how to write CUDA, right? So it's a really, really good building block for you to practice. All right, so that's it. So let's go through what's ComArch, right? And since you all been through my class at the yes, the system skill server is weak, and it's okay. I know. So we just want a relative time. So as long as it's faster, we're good, right? So it's weak. We are aware. Not sure how to fix that. uh, So one quick thing is make sure you test your code on syskill when you want to check for performance, because I'm gonna run it on syskill because your machine and the syskill machine will have a different cache configuration. So you see a different number if you run it locally versus running on syskill. So you might have seen this slide before, actually. I think I asked it at the end. So if you look at this architecture again, right? If you go to Louvre in Paris, this is at night, right around when they close the museum. But if you do take pictures, definitely there's a shot where you can, basically there's a fountain in front. After the museum closed, they closed down the fountain, and you can get this like reflection shots, right? So yeah, it's a really, really fine architecture because the whole block is the museum. It's not just that pyramid. The pyramid is just the entrance. Under there is a really complex museum, right? Including these buildings that you see. Again, another sample, right? I see a Waterfall, right? By the way, this is a hike I did with Ajahn Kanat back when we were younger. This was during the fall season when the leaves changed into yellowish. I was expecting orange. We got that too soon. That's why you see yellow. So, but it's still beautiful, right? And then let's say back in the day, there was like a rich guy, right? Say, hey, I want to build a house on a waterfall. And voila, you get the falling water. It's actually one of the World Heritage sites that you can see is close to Pittsburgh, where CMU is located. So when every time we have a guest coming by, like friends coming by from out of town, we drive there, and I'm so sick of this place. I actually forgot how many times we went there to take people there, right? But it's a really nice house. If you go there for the first time, it's awesome. If you get there for the second time, it's boring. But basically, it's a really, really nice architect, designed by Frank Lloyd Wright, which is one of the really, really top architect of his time, right? There's many, many buildings. So if you look up Frank Lloyd Wright, he designed so many buildings in the United States. And you also have his own like school, and like there's architectural styles that follow his styles, right? Uh, this is basically an architect in real life, right? So if you're asking a question like, what about computer architect, right? So we design computer. We need to understand the circuits, right? And understand the software, who use these software and how they want to utilize it. So we can design a hardware for them, right? That's why, I mean, it's the same as if you have to design an Xbox, right? What would be your primary program running on Xbox or PlayStation 5? There's only one type of program running there. Games, right? What would be the second thing you might have to do? Network, right? You want to make sure you can play multiplayer games so you can bash your friends and troll them when you kill them in the game, right? So these are user demand. You know exactly these are the demand. So you might want a piece of hardware that first is cheap, right? You don't want a full-blown supercomputer running your game. You don't want to blow like $10,000 to buy a game, a console, right? So it has to be cheap. Within like maybe $300 or $400, it should be you should be able to afford it, right? It should be small, so you can carry it around, right? It should be able to render cool graphics because that's the only thing you care about in games, right? Can I render that frame within the frame rate of my TV? And can I generate 4K or 8K resolution, right? That's all, right? What else? Simulating physics. Have you ever think about when you play first-person shooting game, how many physics simulations you actually have to run when you go around the scene and trying to like shoot your friends, right? A lot. And if you do it poorly, you get crazy animation that happen in some of the games, right? The memes like GIF that you and many of us has been using is from fail physics simulation, basically. And yes, it can be a feature. Well, don't call it a feature, guys. It's a bug. It's obviously a bug. Um, but yeah, basically we build machine based on the workload that we run, right? So you know that you do physics simulation, you know you have to do rendering, you know you have to actually talk to the TV, you know that you have to talk to the other devices in the network. Okay? So you can use that. Yes, we at ragdolling is not a feature. Uh, so the other aspect of it is how to evaluate the design, right? You all care about performance, right? We all care about performance. But think about it. How can I compare performance from one generation of hardware to the second generation of hardware, right? Functionality. You want to make sure they function, right? A ragdolling, well, is likely not a feature, right? Uh, so make sure that it works based on the design. Cost, right? You want to make sure the buyer, if I have a chip that costs 5% more than my competitor, no one will buy my chip, right? So cost is important. Usability, can I use it? There are many, many great machines that get built and never sell, right? Because sometimes it's actually ahead of their time. So if you look at the articles that I post as a reading, recommended reading for our lecture for this particular lecture, there'll be quite a few machines that the author mentioned that is awesome, but never get used because it's way ahead of the time, right? So from the business aspect, you want to make sure this would sell, right? Anyone here heard about Intel Larrabee? There was a day and age where Intel was trying to improve the way they deal with graphics application. So Larrabee is like one of the way that Intel designed to handle these tasks. I actually love the design, to be honest, but it doesn't really. I think at the time they scrape the project because it doesn't really meet their business goal, right? And they stick with their integrated GPU. So these are the things that we have to work with the user and make sure that it would sell as well, right? Uh, that's always a key goal in designing a good computer. And our job as an architect is to identify and achieve them. So what would be the role, right? Again, I want to make this lecture lighter. We'll get heavier going next. We will talk about ISA coming Thursday, but today will be lighter. Uh, Now, what would be the role of an architect? So this particular slide I adapted from Yelpat's lecture note, which get adapted into my advisor owner Mutlu lecture note. So owner is Yelpat students, Pat is one of the senior computer architects that everyone in the architecture world knows. He's one of the prominent figure. He did a lot of things on a lot of branch prediction earlier, and then a lot of work on like how to make the parallel programming faster through like making the critical section faster and things like that. So if you're curious, let me know. But the overall role is basically you should be able to look backward. Look at the design that are done previously, programs that are being run in the past, right? And analyze and evaluate these proposals. Are they good? What's bad about them? What's the pros and cons? Look at the future. Specifically, listen to Dreamer, right? There was a time when the AI community dreamed about fancy hardware that can do machine learning, and that never exists, right? That doesn't really exist until they make the GPU programmable, right? When they make a GPU programmable and can run normal program on top of graphics, the ML explosion happened afterward, and we all know how it haven't ended yet, right? But it's still going on. So you need to listen to your friends in the other area and say, okay, what do they demand? What will be the perfect hardware for them? Know the state-of-the-art design and push it, right? Push it further. We were talking about these days. We are actually talking about what if we have a machine that have terabytes of memory, right? Can we have that? If we have it, what will be the benefit? Know the nature of the problem. So this basically look up the compute stack. We'll cover what is the compute stack in a bit. But when you look up, you know the algorithm. You know how the algorithm is designed. So you know the constraint of the software, right? So you can assume certain things. The more assumption you can make, the easier the design that basically the easier your task becomes, right? If you know, oh, I can assume this, I can assume this, I can assume this, then you can make your hardware really fast. Look down, know the technology, talk, not, you don't have to always talk to people who do material engineering or circuits, but these things enable future technology. There are groups that do a computer that can actually degrade. This is biologically degradable computer, right? So that instead of throwing away your phone and become like that piece of metal and basically kill all of us in the future because of global warming, right? We design a machine that after maybe 100 years, it actually will degrade, decompose itself, and doesn't hurt the environment, right? Sorry. We talk about different material to make the memory bigger. We're talking about terabytes of RAM, right? This thing will become the new, basically future technology. All right, now here comes the computing stack. This is what is appearing in, I would say, 99.9% of computer engineer in Thailand. You have the front end, which is I know how to code. I know how to do a web development. And then the back end, yeah, so there's a question on the chat about degradability, about is it material science issue? Yes, primarily there's a material science issue, but when you have these new devices that came out, the constraints are different. So each component would have different features. So you have to redesign to make it fully functional again. Right now, these biodegradable materials, for example, are slower, right? So how can we utilize them? So it's the bridge between material science and hardware architect, which is how to build this new thing, right? And then after we build this new thing, can we map it back to the x86 ISA assembly and make it work, right? Things like that. So let's go back to our compute stack. This is basically what many people in Thailand envision computer science and computer engineering, right? You have front end, you have back end, which is I can deploy certain piece of framework on a server, and I can configure that so that it work. Right? I can configure that so that it just work. Anything below that stack is an alien to them. That's why I put in those alien signs, right? And the thing is, there's a big gap between that and the circuit, right? If you remember from our system skill class, we have assembly, right? And it's not even that far. So if you zoom in, right? If you zoom in theory, this is basically what you're looking at. You have a problem. You use an algorithm to solve your problem. You develop a program based on the algorithm. So I can call this the front end. This is basically our front end, right? Then to deploy, right, you need to compile, you need to run, you need to configure the system. So this is like a shallow part of the compiler and runtime system, right? The depth part is how to do scheduling, how to manage all the threads, how to manage the system. These are not touched by the folks who do back-end development at all, like full stack developer uh, at just the surface of this, right? Beyond that are people who build operating system, modify the operating system so it works for distributed computing, modify how each of the server communicates, modify how you manage the data across server. Why are this important? Let's say you want to deploy IoT, like let's say you want to deploy a smart city, like build a smart city, right? It means you need to build a system. You can't always rely on AWS to handle every single task, right? That's a really short-sighted idea. You have to make sure they are reliable, make sure that certain components are managed by your own system. So you need to know. The thing is, you need to know more of this knowledge. All right. So in our class, we'll focus on runtime, ISA, and microarchitecture. Right now, I'm not going to talk about what are the ISA and what separate the ISA from the microarchitecture. That's for Thursday. But we give this abstraction so that you don't have to think about the logic, device, and electron. Right? That's too low level. Right? So from the programmer point of view, the user design choices impact everything going down. And what we do is to link the top part with the bottom part. That's why I always make the joke that whenever people said back end, that's front end for me, right? That's where they run the application. And that's when I have to manage whatever they're running, right? And now you might think, oh, I mean, I'm just gonna do this software development, right? So why do I care? So the benefit of knowing the hardware is these things. What if your code is slow? It's going to consume much energy. New computers slower, even though you upgrade your computer, right? Program produce incorrect results. Run into segfault. Run the program and it hangs. Somehow your code shut down a computer. It happened, right? What do you do when this happened? What's that one website that we all go to? Just to make sure you're still here. Yes, we all go to Stack Overflow, right? And sometimes you might be wondering, I read the answer, I don't understand what they're talking about. How many times you run into that? You read the answer, it's like, that's unclear. I have no idea what they're talking about. It happens, right? It happens all the time. Stack Overflow sometimes gives a great solution, but without the explanation. That's also another bad thing that can happen. It's like, I guess I can try to copy and paste and try it out, right? But the thing is, at minimum, if you know how the hardware works, it helps with trying to figure out what's going on, right? It tells, well, when you browse Stack Overflow, hopefully it's better. More reasons, advance in hardware can enable new technology, right? Modern day machine learning is actually enabled through the hardware. IoT is one of the things that people overlook in IoT is a lot of hardware involvement, right? You need to be power efficient. You need to make it reliable. You make sure they're fast. Make sure device can communicate efficiently. We can build application with cool graphic video games, right? Other real world example is if you this is your project blocks metrics multiply, right? You make it really cache friendly. When you can do that, it basically means that you can do metrics multiply in parallel, which is, for example, running on the GPU. And it turns out machine learning do a lot of those. That's the main one of the main operations that they do. Multiplying metrics and vector. So these are the key primitives that are being run on machine learning, right? So I can safely say that without architectural hardware advances, there'll definitely be no future in ML, right? We have to basically move the playing fields together, right? Another example is the GPU, right? Have you heard about the A100 GPU that NVIDIA claims, oh, that's the best in the world? Yeah, of course, they're one of the two companies that built the GPU. So of course, their new generation chip is gonna be the best in the world. But it's pretty powerful, right? But you need to know the hardware to actually program and to make sure they're super parallel. And the program need to contain the same operations, such as a matrix multiply, right? Otherwise, it's gonna be super slow. Otherwise, it's gonna be super slow. And this is something NVIDIA never tell you, right? And this is something that many people misunderstood the GPU for. Because these days, there's a lot of PR campaign by NVIDIA that, hey, this is gonna be the fastest computer in the world. Of course, if you know how it works, it can be fast, but it's not going to apply to every single type of application, right? There's a clear distinction between why the CPU work and why the GPU work. I'll give you one example. I was actually in a quite a rather big meeting between many of the leading, I guess, management wing of many university and NVIDIA, right? And NVIDIA basically presenting, and they want more collaboration between Thai University and them, right? And the team in Singapore. And some of the guys are super clueless, right? Some of these like quote unquote computer engineer are super clueless and like, oh, NVIDIA is like basically doing everything. No, no. NVIDIA is good at certain tasks. You need to know what they're good at. Otherwise, if you run every single thing on a GPU, it's going to be really slow, right? Their CPU is not going to be as good as Intel or AMD. That's a fact, right? And there's a reason behind it. Now that they acquire ARM, I'm not sure about the next 2 years. Who knows, right? We will see. But for now, their CPU is basically something lacking. That's why we buy the GPU to plug it on a motherboard controlled by a CPU. There's a reason behind that. Right? So if you know this, you know why you need to buy certain parts, why your workload might require certain piece of hardware, right? Other example is security. Anyone heard about the Meltdown and Spectre vulnerability that was happening around like 3 years ago, 2018? So this is a hardware bug, actually. And anyone wondering what's the key difference between a hardware bug and a software vulnerability? Can you patch a hardware? Can I patch a CPU? I have a CPU, right? And someone discover, oh, I can attack the other program that run on the CPU. And this hardware, it's a hardware problem. Can I patch them? Not really, right? You're just like, oh, okay, out of luck, you can't do much, right? With the software, you're gonna have Linux patch all the time. That's why you upgrade the version of Windows and Linux, right? Uh, well, I mean, yeah, you can't even that, right? You can solder things on the CPU easily because everything is so small. Everything is so small, right? So these bugs basically spark a lot of new interest into, okay, maybe we want to make sure things are secure, right? Because to patch, actually they managed to patch these bugs by disabling some feature in the hardware. Some feature that make your CPU fast, they are disabled now because that becomes the attacking point, right? So you can do product recall as well. That's also a valid option. But how much will Intel lose money? Right? They don't want to lose that much money. So that's one security. Another thing is called like another possible security issue is called roll hammer. And actually, fun fact, this is invented in the lab I was in at CMU. So one of my lab mate, Yoongu Kim, he's right now an engineer at Google, uh, was testing DRAM, right? Testing DRAM and try to see, okay, what's the reliability issues? What's the what's the error rate that can come with like thermal and each of the configuration? So the way we test it is basically write different pattern. That's the same way as when you do mem check, but it's more like a detailed mem check because we write our own controller. And he found that when I write one location data to one location again and again and again and again, it happened to flip the bit of the nearby location. Basically, it means that I can write a program that overwrites some other program's data that just happen to sit nearby in DRAM inside this chip, right? What can you do? Right? These are physics. These are actually physics because when you, I think at the time we were guessing because we don't know enough physics. Uh, we were guessing that when you do this right over and over, it generates current, right? Physics law 101 high school, when you have current going that way, how does a magnetic field go? Right hand rule. Current go that way, magnetic field generated this way, right? You have the magnetic field in your wire in DRAM going that way when you write. And when you do this repeatedly, this magnetic field induce the current to go into nearby cell. So basically electron leaks in, and it leaks in and it flips the bit. Why is that bad? Can I overwrite someone's password with that? If I know the location, then yes, right? I can overwrite pages in Linux and cause blue screen, right? So I can do a lot of attacks based on this alone, right? So this is another thing that becomes a security problem. So what are the after effects of these kind of findings, right? Well, for the Spectre and Meltdown, especially the security flaw in the CPU. So Intel stock went down, the price went down quite a lot. I happen to own Intel stock even now. At the time, it went down, I think about 10%. Not happy. Lots of patches, right? So many optimization being disabled and patched to make sure we don't see these bugs. And it spawned many research that come out of this. How can we make sure everything's secure and still fast? Because those are conflicting goals. I want to secure my data. Right? That traditionally that's come with performance impact. How can we make sure it's still fast? And it's also spawned another discussion on how can I patch a hardware? How can I make it patchable? The roll hammer, the one with the flipping the data inside DRAM, you can look at some of the patch note from Apple in OS X for this particular version. It would say this is the description. They fixed the disturbance error, also known as roll hammer, that exists. And the other thing that I've seen so far is also work done by a team at Google into can I use this to attack Android? And I think they did. They actually managed to write a Java code that exploit this particular hardware security fault to attack the other process running on Android. Right. So these are some of the example. what else, right? So we can build new hardware, totally new hardware. One example I'm going to use is this paper that we published last year. So this is a collaboration work between my colleagues at CMU, researcher at Intel, where she interned at during the summer, my advisor at ETH Zurich, myself, and my friends at UIUC. So basically, we discover, hey, when you do sequencing, what's that? String matching. Right? It's ACTG. You compare ACTG pattern with the reference genome, which is, if you heard about the Human Genome Project, that was a big project that tried to establish this is the default DNA of human and how it looks like. And when you want to test your own DNA and see if you're likely to get, say, cancer or like certain sickness, certain disease, right? You can get your DNA sequence. I'm not sure if you heard about a company like 23andMe. Those are companies that try to also do this, probably not this level, and try to see, okay, are you a mix of like Asian and different like European country and things like that, right? And one of the parts that are slow right now is the sequence alignment. Basically, check where is this sequence of 1000 base pair, this ACTG, belongs in the human DNA so that you can reconstruct your own DNA, your own genome. This is string matching. Basically, we then say, hey, it's a string matching problem. So let's build a string matching hardware that sit next to DRAM. It's not on the CPU anymore. This is basically sit next to your memory so that you don't have to transfer the data back and forth between the memory and the CPU. And we get a thing about like tens and hundreds times faster. I forgot the exact number, but it's actually a lot faster than running this on a GPU and also on a software solution. So that's another reason. What else? There's right now a high demand, right, for people who know computer system and architecture. Because why is that? A lot of people have close to zero knowledge of how computer actually works. If you graduate from a CS degree program in Thailand, I can assure you, you know how to do web development. I can assure you that you can have the full like basic data structure. You know how to design an algorithm. These are default, right? And you have so many professors who are expert in those areas. You know how to use certain libraries, right? You know how to develop a website. Not many of them know how to optimize their code. Not many of them understand how to analyze the bottleneck and make things faster. Not many of them can scale the program. There are so many things that crash in the past 2 years I've been in Thailand, and it feels like these are basic. Like it shouldn't crash, right? Uh, you can further optimize popular workload like ML, AI, all the keyword you've seen so far. Right? Knowing the hardware will allow you to basically be that guy who can write code that's much faster than your alternative, right? Another thing is like, for example, why are you spending so much money to buy a fancy new GPU when you can optimize the old one, right? You don't have that much money to spare. We are a pretty poor country. I will face that fact, right? Even more reason. So I actually, for the purpose of this slide, I think I'll pause the recording. Okay, so we are done with the why do we learn these things? So let's go through another lighter material before we go deeper. Is what is a computer, right? So this is basically intro into what are we trying to understand here, right? So if you define a computer, basically this is the dictionary. I think it's this Oxford dictionary definition is an electronic device for storing and processing data. And that's the key. I will just take that first line. According to the instruction given, that's all. We give instruction, the computer spits out and process. give us back the results, right? What would be the difference between a calculator and a computer? Anyone want to take a guess? How can I differentiate between, can I call this a calculator and can I call this a computer? So can you program a calculator, or do you have to actually? I think both can do math stuff and return math stuff, right? The thing is, in a calculator, in many cases, you don't really program them, right? Yeah, yeah. So that's a fancy calculator that comes with its own chip. So you're talking about this scientific calculator, this fancy one that can be programmed. They actually have computer chips in them from TI that works. So that's actually more the programming side, right? But if you take a deeper look into this, if you take a deeper look, you're looking at logically, you have logic gate and or X or not, right? That built together that becomes your ALU. Oh, a bit of last slide here. All right. Sorry, audio got cut off. Hopefully nothing to do with that pause and resume. Basically, the computer is capable of being programmed. A calculator, basically, more of the time you think of a calculator, you put in the inputs, you know the exact function that you want to run, right? You compute that. You, as a human, gather the output, then feed in the next command, right? And the deeper look into that, the logic gate is put together with the control signal, right? And becomes things like the ALU, the arithmetic and logic unit, the one that is the brain of the computer. The other element is the storage element. Where do you store the data? There's a DRAM, right? There's memory, there's storage, the hard drive, SSD. There's also network drive, things like that. But physically, it's just a bunch of transistor, capacitor, resistor, wires, right? It's just a bunch of things that somehow, once you put them together, it means something. Which kind of means that there's an element to make sure that somehow your program int main, right? Printf, it means something, right? It means something to this transistor, and it's capable of running something, give us back results. So a deeper look into this, you have the processor, right, that do the data processing. There's a control and data part, and I'm gonna go into more details in the lecture number 3, if I remember correctly, on what is the control and this data part. But basically, these are what control your CPU and what are the elements of the CPU. Data part is the hardware inside the CPU. Control is how to control the hardware. The memory is where you store the program and the data. This is one of the key methods that I want you to get out of system skill. If you haven't got that, that's where you store program and the data. It's all in your memory, DRAM. And then there's an I/O, right? Storage and devices. And data are basically being transferred across these elements. You bring data from the file into the memory. You bring the program into the memory, run it in a processor. A processor spits back the result. The result is shown on your screen through the I/O, right? Okay, so that's basically the basic of computer. So let's talk about the history part, right? Again, light material. It's been around for a long time. Right? You have this thing called mechanical calculator. Anyone here heard about the Jacquard's loom? Anyone know what is the loom? If you don't know, look it up. Yes, you use it to weave the fabric together, right? You weave the fabric into a piece of clothing, right? And once you have this clothing, I mean, what's the next thing you want out of the piece of fabric? You want pattern, right? You want to be able to actually use different pattern. So Jacob's loom is a programmable loom. You have punch cards here, right here, that make it programmable. Based on the pattern, you can create different different pattern on the clothing, right? It was invented back in the day, right? And it's awesome because it's a mechanical thing that are now programmable. You can control them, right? There's a control element. There's like basically processing the data looms that come in. These things are called each of these here thread, right? Remember our old friend thread? These unit, a bunch of thread grouped together is actually called a warp in the Jacob's loom. Anyone want to get a guess on what else are being called a warp? Oh, I didn't know that. So the sabotage comes from that. I didn't know that. Yeah, but a warp is a group of thread. If you see it from a picture, right? NVIDIA use it to call the exact same thing. A group of thread in the GPU is called a warp, and I think it has a context that comes from this particular machine. All right. ENIAC. So this is I got lucky. I was visiting UPenn, so I get to see the actual thing on display. So this is the ENIAC machine. So for many of you, you might have realized that this is one of the, well, it's the first computer, right? It's the first digital computer. There are many machines that are computer, but they're mechanical before this. Uh, yes, I'm gonna talk about it actually next slide. So ENIAC is like the first digital programmable computer. It's digital, is actually extremely fast compared to the other computer of the time, and is invented by Eckert and Mosley, sorry, at UPenn. Consists of multiple vacuum tubes, and it weighs a ton. Like actually not a ton, 30 tons. And you can do a decimal digit operation. Right? So instead of binary, I think it's worked with decimal instead. And it's programmed using these plugs that you see, right? And fun fact, for people who do architecture, if you are one of the like really top architect, like basically it's a younger generation. Basically, there's an award called Eckert and Mauschy award for people who contribute, like for basically young professional who make high contribution to architecture field given each year in a yearly basis. So that's actually where it comes from because they invent the first computer. Uh, and now come back to the question of what about analog computer, right? There's ancient machine in Greeks, mechanical calculator. Jacob's loom is actually another mechanical computer. So let's look back in the day, and you might have seen some of these in movies. Actually, there's a lot of hardware advances. Uh, there's a ABC machine, right? In Germany, the Konrad Zuse invented C3 and C4. Fun fact: C3 get bombed to shred by the airstrike, strike, I think, but they reconstructed later for the purpose of basically conserve the invention in the 60s. If you watch, anyone here watch Imitation Game? So in the movie, right, Turing was building the Bombay. The Bombay was used to decipher the Enigma machine. Basically, the encoding that come from the Enigma, basically the cipher machine, right? And the Colossus is the follow-up to the Bombay that comes afterward, by the same group of guys at the the British side, right? To decipher another cryptic text. So it's a different encryption algorithm that Colossus is being used to decipher. I believe, I might be wrong, I believe that some of the observation that you've seen in the movie, like some of the letters are used more often, right? The letter A, E, I, O, U, and are going to be used more often than the letter C, right? So that works for the Bombay. They use that observation to decipher the text. With the Colossus, the new ciphertext doesn't have that property anymore, so they have to invent another computer for that to crack the code for the German. From the German, not for the German, my bad. And then there comes the ENIAC, which is the digital solution to this mechanical computer, right? So in the movie, again back to the imitation game, you see that there's a circular clock that rotate around, right? So this ENIAC kind of replace all the mechanical part; it becomes electric. Then von Neumann comes up with the EDVAC, which is a different machine, and then the EDSAC by Wilkes is the first store program. What does it mean for a program to be able to store itself in memory? How long have we been using this? It's a long time, right? So we use this a long time because the abstraction of everything is inside the memory is nice. You have this memory and it manages everything, right? So you can store the program there, you can store the data there. Good. Right? You don't have to actually use switches and plug anymore to program. Now it can be stored in the memory. And then there's like IS Bigelow, and then afterward, after the 50, right? Basically, there's an emergence of software. Fortran is invented in 1954. And why is that nice? Now you can program. Now you can write code in text rather than in punch card and switches and plugs. Now you can write code in text, right? So this is nice. This basically means that the computer is digital, programmable, and can compute a lot of things, right? So here comes the age of Moore's law. Anyone heard about Moore's law? So Moore's law basically said, hey, every 2 years, the number of transistor will double. So this changed a little bit with modern day and age, right? There's so many electrons you can store in the transistor. So when you go to like sub 10 nanometer, you need to make sure you can still sense those electrons. So it can be challenging. So there's a paper in 1965 that Gordon Moore, which is one of the CEO of Intel at the time, right? He was actually writing these articles and he was plotting number of transistors that Intel was able to produce so far, right? And he thought, hey, it's double every couple of years. It's also a running joke that because Gordon Moore owned Intel, so the engineer there need to make sure they keep up that trend. I need to make sure I double that every time, every 2 years. So I'm sure it's insider joke. It's not true, but it followed this trend pretty closely, right? Why do we need transistor? It means that we have more complex CPU. It means that CPU is faster, right? Between I would say a Pentium 2 processor and your iPhone, which one do you want for your computer? Your current iPhone. Not you don't even have to be current one. Let's say A9, like so 4 years ago, I think. Which one are going to be faster? It's the A9 is going to be faster than Pentium 2, right? It's much the components that go there is much smaller, and there's so many more transistors that you can pack into that tiny chip. So why more transistor? Because program wants more performance. Transistor is a resource that can be used to address bottleneck. When I said can be used, that's the important part. you need to think about what to put in. The design part has to be still implemented. What do you do with those transistors? But rinse and repeat, right? You can keep inventing. Those are one of the. So I think this is a paper in 2000. If you recall 2000, that's a day and age where single core kind of dominate the market, right? You have Pentium Pro, Pentium 2, Pentium 3, Pentium 4. They are all single core processor, right? So from the research point of view, Yale Pat, again, the same guy that I mentioned earlier, write this articles that talks about what else should we do with computer, right? How can we actually deal with the fact that you can't scale a single core processor anymore? This is called Dennard scaling. This is different from Moore's law. Dennard scaling has to do with you can't build such a big single core processor. So it becomes multi-core. Then what would be the bottleneck, right? If you look at this paper, you see that many of the prediction that he put in the paper became reality because you know what application is going to happen in the future. So you know what will be the demand. So in modern computer, there's many diverse type of computer. You can have this Raspberry Pi, right, for your IoT class, right? You can program. You can actually put Linux in that thing. One of my friends actually installed like I think SNES emulator and hook it on a TV, and it works with the TV, right? It doesn't even need a lot of programming. It's a bunch of like open source library, and you can install these things. You have the GPU, right? This is the older generation. Because I'm lazy, I don't want to update my slide. But yeah, you can use the GPU to render graphics. You can use it to run machine learning, deep learning application. These are a picture of one of the cluster at Lawrence Livermore National Lab in the US. As you can see, these are Blade computer. It's a bunch of server, basically. Think of this thing as like a tiny fraction of like one SysQ machine. And imagine how much compute power you can get out of that, right? iPhone, again, old picture. I don't want to update it. Single lens still has the touch sensor that I can unlock instead of using my face. These are another type of computer, mobile phone, right? We call it system on chip. It has multiple type of hardware. It has a CPU. It has a GPU. Has the machine learning chip. It also has its own security chip. So whenever you use the anything that related to keychain, identity like your face ID, touch ID, it can be stored by passing the OS. They make assumption that I cannot even trust the iOS. So when I can make that assumption, it means that well, if my iPhone got hacked, right? Let's say I go crazy and I jailbreak my iPhone and it got hacked. They can still cannot access my this security key, right, from my data. You can have a GoPro, which is another system on chip. Most of the processing goes into things like video processing, dealing with storage elements and making sure they don't break. Actually, these things are pretty sturdy. Surprise! I took them through hiking in the Narrow in Zion National Park. We literally hike on the river, and it survived, right? With, without any scratch or anything. So these are designed to be super reliable. It can tolerate temperature that are going a little bit more crazy. If you use an iPhone in a freezing temperature, you might realize it will not boot up. I ran into the example where I want to watch a hockey game. So one of the things in Pittsburgh is uh, Pittsburgh is blessed with right now really two really good sports team. One is the Steelers, is a football, American football team. The other one is the Pittsburgh Penguin, which is the ice hockey team, right? And at the moment, we have quote unquote the best player of the generation in the team. Imagine you have a Messi, like, in the team. in your local team. So I went and watched the hockey game, right? Turns out it's too cold. I cannot boot up my phone and I cannot print the ticket. So I actually have to warm my phone up in the car for a while until I can boot it up. But the GoPro will not run into that problem. The chip and the hardware are designed to tolerate those kind of temperature. What is this? Anyone want to take a guess? See, and some of you might have seen it. Quantum computer, right? I use this slide for the system skill again, right? Um, so in this class, we'll actually talk about what will happen when I run the program. It actually does look like the arc reactor, to be honest. Uh, Great comment and great catch. uh, yeah, so let's say I have this code, right? Just initialize I to 10, j to 20, and I do k equals I plus j. There's going to be a lot of things happen in the program, compiler, runtime. Again, same slide from system skill, right? Over here, the class will also talk about how can I make this faster, right? And before I wrap everything up, I'm gonna talk about the von Neumann model. Anyone here heard about the von Neumann model? All right, awesome, because I cannot tell whether this thing has already been covered in system skill or not. So remember von Neumann in the 40s and 50s of computer? Von Neumann is one of the major figure back in the day. He's made so much impact. And one of the impact that he's making was like, how do we program? How do we actually think about the programming language, right? And I can assure you, everyone used this model so far. For now, how many of you here took system skill before? I mean, no, not system skill, parallel programming. Parallel programming. So over there, we talk about the data flow model. It's a different programming model, but C, Java, my cat is going to make a big jump. I want to make sure she doesn't fall. Give me 1 second. All right, so uh, so von Neumann model is where you store a program in the memory, and you have a program counter pointing at the current instruction. So that's a von Neumann model. Basically, everything, most of the programming language that you use nowadays will follow the von Neumann model. There are two key properties. The program is in the memory. The program is in the memory, and it's linear. Why do we want them to be linear? Why do we want instruction to be linear in the memory? So what's the, yes, that's one of them. Easy to retrieve. You exactly know when I finish this line, the next line is the next block of data, right? So that's why making this linear is nice. I know that if I increment my PC, that's the next the next line is assembly. If I increment the PC again, that's the next instruction, right? And memory is unified between instruction and data, right? And your program, you have a program counter, look at the memory and process it. That's it. Simple, right? Simple, and make it sequential. This is called sequential instruction processing. We process one instruction at a time. Fetch, execute, complete. Fetch means I go to the memory, get that instruction. Once you have the instruction, the next thing to do, run it. Completion means that I store the output, right? I process the output, go to the next instruction, and then process the next instruction. So the program counter, or the PC, or sometimes we call this instruction pointer, right? Pointer in the same context as pointer in C language. It points to something. What does this pointing to? Point to instruction. So the program counter or instruction pointer is the same meaning. Advance to the next instruction, except when you have branches. What are branches? If else, for loop. Otherwise, you go to the next line in your code, right? That's it. That's the von Neumann model. And the way it works is you have so this is your DRAM, right? This is say your SSD, hard drive, keyboard, right? Your output can be your monitor, right? These things is your CPU. The way it works is inside the memory. The memory is accessible by saying, I want to get the data at that address. So I give the address, retrieve my data, right? So the input talks to the memory because you put the program there. From the hard drive, it's stored there. Then the CPU talks to the memory. Similar to what we learned in system skill, right? Every time we see a pointer, it's a memory location, so you go to the main memory. The CPU internally manage the program counter and what we call the register, which we'll cover in the next lecture. What are these registers? But we kind of cover that in system skill, right? The RAX, RBX, these are register. Remember our old friend RBX, RAX, ECX, and all those things. These are really fast memory that you can use to store and retrieve data. So the CPU processed this. The dashed line that I draw here are the control signal. CPU will tell the other guys like do this, do that, do that, do that. Basically, CPU kind of gives the control, right? And inside the von Neumann model, is this the only model? Nope. But this is one of the most dominant because it's easy to program. It follows the way human process instruction, right? It's similar to, let's say you were being told to do something, you're being taught to do something, right? If I'm teaching you something, I'm gonna say, step 1, do this. Step 2, do this. Step 3, do this, right? That would be easy. You just go to step by step at a time. What if I say, I give you a blank assignment and say, that's my desired output, here's a function, good luck. It's gonna make it more challenging, right? Because I didn't process into like, what are the steps that you have to do? And you can tell, right, from, for example, the cache lab that we did in system skill, right? I didn't give you a concrete steps. So there's lots of questions. And that was intentional, but you can imagine if I can write things in steps, step 1, step 2, step 3, it's gonna make it a lot easier to take all the challenge out, right? And all major instruction set architecture, or ISA. ISA is basically a language that talks to the computer. It used this model, right? x86 use it, ARM use it, MIPS use it, Spark use it, Alpha use it, Power, IBM Power, which also used in IBM supercomputer, also use this. What would be the alternative? The alternative is called the data flow model, where instead of fetch instruction in a control flow order, right? You go to the next instruction, right? Data flow follow the data flow order. Do I have my data? If I have my data, I'm run it, right? I don't care what's the order of instruction. I have my data. I run it. I will run it, right? There's no instruction pointer. Ordering is based on the data flow dependence. Think of it as a mass function. And many instructions can execute at the same time, which gives you parallelism. But we'll cover this in the functional and parallel programming class because the next time data flow model will come back and haunt you is either that class or the next computer architecture class where we would tell you how can we design a program. I mean the CPU that take in von Neumann but run in the data flow model, which is faster. Right? These are the next topic not covered in this class. So if you want to learn how your chip work really, That'll be in the next material, basically. Some more basic stuff, right? So we should be covering basic digital design, something like wires. So anyone here heard of wires? Anyone know what it is? If I draw single line, what do they do? Well, it allows electrons to move around, right? Yes, you use it to charge your phone as well, right? Uh, so if I put a value here, let's say I put a value, some data in a wire, right? In the wire. If you have one single wire, it's gonna be 1 or 0, 1 bit. If I have 10 wires, it can be 10 bits, right? What does it mean? It means that everywhere, if I sense the value, I'll see the same value. This wire behaves like this. Basically, if I draw a line and say that's your address, at every point in that wires, you see the same value. That's all. Basically, if there's a line in the diagram and I say that's the address, it means that the address is propagated everywhere. Everyone will see the same value at any given time. At any given time. Register, sometimes I would draw it like this. Right? In, out, I guess ID that you want to say. So let's say I want to read RAX. I would put in the value 000. It would produce RAX at the output port. Basically, that's it. I can store things in there. I can read things from there. It behaves like the register we learned back in system skill class, right? So that's the only assumption I have to make in this class. What is the clock? What do we use the clock for? It, it can be used to tell time. Perfect. This makes everything digital, right? The digital part is when we can tell time. We move one clock cycle. It means that I'm going to move and proceed to change, for example, the value in my wire from value 1 to value number 2 after the first cycle. After the next cycle, I can change it to value number 3. For the input, it can be input 1, input 2, input 3, right? I use this clock to tell when I can send each data. Without the clock, how can I coordinate across all these components, right? How can I tell that's going to be value 1 without the clock, right? So the clock, if you look at the signal, basically alternate between 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. This is one cycle. This is one cycle. Within that time, I can send data around and make sure I hold it. I hold it like that. The next cycle comes in, that data that I hold can be stored in certain components, and then I can hold a different value in a wire, right? So these are the things I can do with my components. Basically, these are physical components on your computer. Gates. These are the AND gate, the OR gate, NAND gate, NOR gate. So AND gate looks like this. A, B. The output is A and B. OR gate would look something like this. A, B, and this is the result of A or B. NAND, you put a dot at the end. Dot mean not. So this is A and B. The output is you do A and B and then not, right? A NOR gate, as you can guess, this A and B, you would do A or B and then you not the whole thing, right? So that's the gate. It works like a typical logic, right? Mux This is likely a new terminology. This is your switch case. If this is basically switch case, right? You have multiple input, 0, 1, 2, 3, and then you select, and then you output. Input 2, input 3, input 4. Depending on the value of the select. If the select value is 0, I'm going to forward input 1 to the output. If select is 1, I'm going to forward input 2 to the output. If select is 2, I'm going to put input 3 to the output. If select is 3, I'm going to put input 4 into the output. Basically, it's many input coming in. You select which one you pass it through the output. All right, any questions so far? This is one of the most important new component that is needed for the fourth lecture. To make sure that we understand that you can build this thing. This is switch case, right? If this select has this value, this input goes to the output. That's all. Demux is the inverse of that. Demux is I have one input, I demultiplex into multiple output. This is basically so I can like spread out the signal, right? And to be honest, the way you can design this component is flexible. You can design it in any way you want. You can have like two inputs. Sorry, my cat again. You can have multiple inputs coming in and select each of the output manually based on the input select, right? So that's it for the basic digital design. And I'm gonna cover this again when I draw these things. Oh, that's a great question. Is the input and output only 0 and 1? It depends. You can make it 8 bits, 1 bit, 32 bits. It's actually variable. You can design the way you want, right? You can make it 16 bits. You can make it 8 bits. You can make it 32 bits. You can make the input, for example, over here 32 bits, and then 16 bits go out of here. The other 16 go out of here, and you can kind of like design this component on your own. When I have the cross with the number n, it means that these wires will have these many bits. All right, so hopefully that answered the question. So basically that's how can you represent the logic part, right? Uh, Data representation, I don't think we have to cover much of this because it's been drilled over in system skill. Everything in program involved is the data, right? Data as an input, data as an output. Data is represented in binary. Anyone want to guess why? It's a voltage, right? Low and high voltage. Imagine you have to sense between 0 voltage and 1.5. How many lines I can draw to the point that I'm going to be inaccurate in sensing? Not much, right? So the safest way is I cut this in the middle. Anything here, high voltage. Anything here, low voltage. Yeah, it's easiest way to represent the data, right? To handle the data, right? Data being moved around involve changing of the voltage. This is done across your wires. If the wires have high voltage, it can be 1. Some architecture treat high voltage as 0. It depends on the designer choices. Sometimes this can impact the energy efficiency quite a bit. Sometimes it impacts slightly on how fast can things be. Storing the data also involves maintaining that. So what is a physics component that can maintain things? So we have wires, right? You have transistor. We have capacitor. We have resistor. So if I want to maintain an electron, which one of these components can I pick from? So to store data, to store electron, right, by default, you can use a capacitor, right? That's what the name suggests. There's also a trick that you can use a bunch of transistors to store electron as well. That's what we use for the cache. We are not gonna go into the detailed design of this because it's out of the context of the class, but it's possible too. In fact, new type of memory use resistance to store the value. So these can be possible, right? This can be possible. Uh, reading the value, read the number, reading the data involve measuring this voltage. Essentially, that's all. I read, is it 1 volt? Okay, value 1. Is it 0.5 volts lower than 0.75? Value 0. 1.5 volts, that's value 1. 220 volts, your computer is fried, right? So depending on what you're reading, that basically becomes your data. The writing data also involves changing the state that you're storing. Are you storing high voltage or low voltage? That's all. Everything in your program is the data, including the program itself, right? And that's it for today's lecture. As I promised, is pretty light. Everything here is background. There's less likely to be a chance at all that anything here will be on your exam. But it's good to know. It's good to know, especially the last part of the lecture where we talk about what is the wires, what's the gates, what are the muxes and demuxes, because these are the main component that we will be using going forward to explain how you build a CPU, right? So hopefully you're all excited to learn how the CPU can be built. And welcome to, I guess, the new ComArch at MUSC. And that's all for today. Any questions? Feel free to open the mic and ask. And let me stop the recording right here.